Welcome back. I'm delighted to introduce Marie Bohmann to talk about tools for understanding topological coHochschild homology.
Thank you, John. Pleasure to be here. So all of you obviously came to Catherine Hess's talk last week, and all of you obviously remember everything she told you about topological coHochschild homology, so I'll jump right in. It's not true. So anyway, this talk is about topological coHochschild homology in more or less the same sense that Catherine talked about last week. So if you do remember everything, you can keep those thoughts in mind. And if you don't, I'm going to define it, and it's going to be all cool anyways. All right. So topological coHochschild homology, from basically here on out, this is going to be called coTHH. Because T coHH is fairly unaesthetic, so we're going to go with this one. So what should you think about when you think about coTHH, topological coHochschild homology? Well, you should think that it is dual to THH, which is why this is maybe also good terminology. And what should you think about when you think dual to THH? Well, you should think THH is some sort of theory for algebras. And this is going to be a thing that we do in theory for coalgebras. So we'll plug coalgebras into coTHH. But some other fun things we should tell you. Defined, at least the way I'm going to define it, it's defined by Hess and Shipley. And let's see, it generalizes, so the T stands for topological, so it generalizes a non-topological, that means an algebraic version of coHochschild homology. That's due to Doi and studied by Gerhardt and Waldhausen, among other people. And maybe one reason why you might care, if Catherine didn't convince you last week, is that there's a close relationship which I'll say at least a little more about to THH and to these spaces, at least in the case of suspension spectrum. So this is like a brief overview of coTHH. So what's the plan for today's talk? So I'm going to define coTHH and give some sort of abstract results about coTHH in certain settings. Then I'm going to talk about a spectral sequence and coalgebra spectra. So some of the stuff will be closely related to what Catherine talked about and some of it won't. And so if you don't know what she talked about, you won't know which is which, but it'll still be okay. Alright. So as I said, the first thing I'm going to do is define coTHH. And since I told you it's dual to THH, I'm going to start by recalling the definition of topological Hochschild homology and then just dualize it exactly. THH. So what's THH? Well, generally, THH is a thing that we do to ring spectrum. Right? We have a ring spectrum, and then we define this invariant of ring spectrum called THH, which is like Hochschild homology for rings. But I'm going to take the slightly more general idea that, like, really what you want to do is think about THH as a thing that you can define for rings in a place where you know how to do derived things, right? It's a derived version in some sense of Hochschild homology. So it will work in a suitably nice nodal monocategory. So for the moment, I want to take that to be my, where I know how to do some sort of homotopy theory. I shall call C. So when we do, we take A and C to do some algebra. And to define topological Hochschild homology, I define a simplicial gadget. Dot and A. How does it work? In level n, I take a bunch of copies of A, all tensiored together, n plus 1. So this is my simplicial level n, and then I have some face maps and some degeneracy maps. So the face maps are given by multiplication. Right, so I can multiply like these two copies together and those two and so on and so forth. And if you're counting, very good at counting, you'll see that I'm missing one. And I need to have the last one, I'm going to do something slightly different. I'm going to wrap this last bit around, multiply it with the first bit. So it goes in a little circle. So the last one is twist and then multiply. And the degeneracy maps. Well, if I have n plus 1 copies and I want to get to another more copies, I just shove in a unit in sort of any of the possible spots. Suppose my algebra was unit. Great, and so then THH. This is the geometric realization. Realization. Which we can think of as the homotopy colimit over delta in the simplicial category of our simplicial object. So what have we done? We've built a simplicial thing from our algebra, basically using exactly the structures that algebras have, right? Algebras are things where I know how to multiply and I have a unit and I just use that as many times as I could, and now I have a simplicial thing, and then I geometrically realize it. So you say this should be a thing that I should do to algebras, right? All of its algebra-ness. So now we get to take the perspective that for coTHH, we're going to start with a coalgebra, and we're going to do all of the coalgebra things that you can do to it, and it's going to be exactly dual to the THH. coTHH. So again, C is our monoidal model category. And C in C, sorry, everything is called C when you work with co-things. It's a little bit of a problem. So C in C is a coalgebra. So let's be sort of explicit about what is all the structure that I need a coalgebra to have. So we should have a co-multiplication. And it should have a co-unit. And these guys should satisfy appropriate compatibility diagrams that are dual to the ones for algebras. So, for example, I'm going to want it to be co-associative, co-unital. I also want co-nilpotency sometimes, but we're not even going to worry about that. Okay, and so then, once I've got this structure of a coalgebra, I'm going to build a co-simplicial object exactly as I built a simplicial object from the structure of my algebra. So, that's what I call coTHH. And so in level n, This is again n plus 1 copies of C closer together. And now I have coface maps and codegeneracy maps. So the coface maps are co-multiplication. So there's your co-multiplication. Or the last one is going to be co-multiplication and twisting. And the codegeneracy maps they're going to come from the co-unit. And because this whole like co-multiplication and twisting thing, it's like hard to keep track of the orders, I'm going to actually tell you the formulas for these guys in this case. So what are the formulas? The formula is that the kth coface map looks like, here I have to get my indexing right, so I'm supposed to do the identity a whole bunch of times, k times, and then I'm supposed to co-multiply. So that's going to increase my number of c's by 1, and then I have to do the identity on however many times there were left, which turned out to be n minus k times, and this works when k is between 0 and n. And then the other one, the fun one, is that so when k equals n plus 1, so my last one, what I have to do is I have to co-multiply and do a whole bunch of identities. It's n times, right? So co-multiply the front one, do n identities, and then I twist around. So it's a twist. I'm going to twist the first copy of C with the remaining n plus 1 copies. So this is the thing that psychologically this is exactly dual to what you did here. You twisted round and then you multiplied, but of course that means you have to co-multiply round and then twist or something. So it goes in the opposite order. And at least for me, it felt like why is this the right thing? But it's the right thing because it's dual.
Yeah, that's in the right order.
I think I do. I think like first I have to co-multiply and then I have to twist, or do you mean these ones?
No, I'm worried about k equals 0 seems, on the top formula seems to be this.
But I didn't twist. This is why I think it's
tensor
confusing.
delta or delta tensor identity? That's the question.
I think it's delta tensor the identity, and this is the thing. This is why I wrote it down, is because I find it confusing. And so then I wrote it down, and I'm like, now I know what it is. But of course, now I can't tell you why I know what it is. but I'm pretty sure this is what it is. Okay, and so then the obvious thing to do is to define. Now we've got a co-simplific it. Let's define coTHH of C to be, well, we should define it to be the homotopy limit. It's a simple category of this co-simplific one. And under nice conditions, like say read fibers here, this is going to be co. I've been very lax with telling you all the things I might want to assume about my normal model category, and so you might or might not be like always the same, or I might need some conditions to make them the same. And maybe I want to assume something like C is fibrant, so that this is homotopically a sensible thing to do, and stuff like that. But I won't belabor it. All right. So now you know all about coTHH, right? Here's that. So let's talk about some context, some C's, as in the category that you might want to work in here, and what happens in these categories. So I could just look at coalgebras over a field. And then if you sort of massage this definition appropriately, you can make it degenerate into exactly the usual notion of coHochschild homology. Or maybe I should put usual in quotes because nobody thinks about this, that I hadn't thought about this before. and this is usual coHochschild homology. You just join. In this case, of course, maybe putting the T in coTHH is a little bit unreasonable, because there's nothing really derived about the usual definition. So, but I'm not going to focus on that one. So I'm going to keep my T. You might think about D coalgebras over some field. And then you get coTHH of D coalgebras as studied by Hess, and Scott. Of course, another example that you might want are coalgebra spectra, obviously desirable. And so for that, I could work in, say, symmetric spectra or S modules or orthogonal spectra or what have you. And so an example would be if I take a space X and then I look at the suspension spectrum of X, then the diagonal map gives me a co-multiplication pair. So the diagonal map gives me a coalgebra structure on the suspension spectrum of my space. So those are some examples. Work of Maximilian Papus and Shipley says that these are basically it in this kind of dev context. So what do I mean by more or less it? I mean that, if I require that I'm working in one of our nice model categories of spectra that we can do brave new algebra in, and I would like a strictly associative coalgebra spectrum, then it turns out to admit a level-wise projection from the suspension spectrum of its zeroth space as coalgebra, which in particular implies that it has to be things like commutative. And so it really wants to be a suspension spectrum. I mean, I think I don't prove that it actually is, but it's, in particular, it's not like a hugely general thing. Maybe a comment about one thing that might be happening there is that we built in our smash product to these sort of nice monodal model categories of spectra, which was like maybe the point of building them. We built it in such a way that it was going to do really good things for algebras for us. Like that was, to my understanding, that was the goal of building awesome model categories of spectra. And so maybe we set the whole thing up for algebras, and as a result, we set it up so that coalgebras are not going to be our friends here. So this is maybe a limitation of our model categories, but I don't have a really solid sense of exactly how far we could push that thought. I should also say, though, that in this case, for suspension spectra of spaces, the coTHH is a thing that we like. So work of Hess and Shipley and Malkovich and Kuhn. So Malkovich credits Kuhn, but Kuhn doesn't say exactly the same thing. And then Hess Shipley extended a little bit what Malkovich did. Says that if X is simply connected, or maybe no code relation, then coTHH of the suspension spectrum of X is the same as the space we know is equivalent to THH of the base group space. If I like actually had a base pointer, you could do that. So this is telling you in particular that we've got some sort of connection between THH, coTHH, and group spaces. These are all really related constructions. Any questions? Okay, so this is like things, the definition of coTHH and maybe some brief connections to things you might have already thought about. So what I'm going to talk about now are sort of, this is the computational tools or tools for understanding part of this talk. So I'm going to talk a little bit about ways to approach understanding coTHH in certain contexts. So I'm going to eventually make my model category specific to a couple cases. But before I do that, let me sort of set the stage psychologically by telling you something about Hochschild homology and topological Hochschild homology again. So for both of these cases, so for Hochschild homology and topological Hochschild homology, the result is the Hochschild-Rosenberg theorem, the HKR theorem, which maybe I don't want to tell you what it is exactly. For Hochschild homology, I can think about it as identifying, say, Hochschild cohomology with derivations, or Hochschild homology with Kähler differentials. For topological Hochschild homology, this is a result of McCarthy and Venesian that identifies THH with THQ. So these are sort of key ways that you want to try and understand maybe what these things are doing or how they're related to other constructions. And the point I want to make is that for both cases, the way that you sort of start really thinking about proving these theorems is you start by understanding the special case of these theorems where your algebra is free, by which I guess I mean free polynomial. So it's in quotes, in spectrum maybe it should be in quotes. So what do I mean by that? I mean like the free graded commutative algebra on some generators. And that's like the easy case for the HKR theorem in either context. And then if I want to prove sort of a stronger result about smooth algebras or something, then I have to sort of bootstrap up from there. Something like that. So this tells us that we want to understand coTHH, we should think about what on earth happens in the dual case and the co-free case. So that means I need to be in a context where I can define what a co-free coalgebra is, right? Like there's some arbitrary model category, like who knows if it even makes sense to talk about co-free coalgebras. And in fact, it doesn't always make sense. So we need a functor. So this is going to be a co-free, co-commutative, co-associative, co-nil, co-algebra functor. I'm going to call it Tim to remind us about the commutativity part of this, C for the co part of it. So this is the functor applied to some x, or x in my category. And what you should think is that when you want that this, what does this look like? You want this to look, I want this to be a really wavy line and not a weak equivalent. I want it to look like, I want this to look like something like the direct sum over n of the number of copies of x times itself n times, and then I'm going to be taking the sigma n fixed points. So it should be it should be given by these sort of fixed points inside n-fold tensor powers of all the things. Like this is like a tensor algebra, except that I'm taking fixed points instead of orbits. So in that sense, it's dual. So maybe some things have to, in order to make sense of this statement, you need some things like you need to know that this really is a direct sum. I really want this to be both a product and a co-product, like isomorphism. So that's going to be something that has to go into here. So to make this work exactly, we need products to be isomorphic co-products. And I need some good stuff about, so I can maybe define this guy, but I need it to be a co-algebra, and so I have to tell you what the diagonal is, what the co-multiplication is, and I can't just do that. I'm going to write it down. But I need some conditions about how the fixed points here are going to interact with these sort of different factors here. I need them to behave like as if these were just a bunch of stuff in sets, and I was going to take fixed strings of elements. If that works, then I can actually define the co-multiplication here. So some good stuff about fixed points for the various symmetric groups have to happen here. These good things do happen in the case of like DG modules. So these are okay. DG modules. Everything works. Great. So in that case, so if I have this nice co-free, co-commutative, co-algebra functor, then you can say the following. So we have this functor, then so if I want to take coTHH of a co-free co-algebra on sub x, then this is the same as the homotopy limit. Here's the thing that I can do. So I can take my x, and then I can take coTHH of x itself, but what do I mean by that? X was just like a GG module or something, not a coalgebra. But I can use a diagonal map for my product and take sort of the coTHH co-superficial gadget with respect to that. Then I can co-algebraize the whole thing using my co-free co-algebra functor. And now then I can put the limit there. So these are the same. Of course, what you'd really love is if I could like kill the dot and kill the homotopy limit and be like they're the same that way. But in general, the homotopy limit is going to be in your arbitrary model category. Like that seems like way too much to ask. Understanding that homotopy limit. But somehow that's what you want to be true. And this is what is true. So maybe let's like go down from our really abstract heights of arbitrary vanilla model categories and talk about what actually happens in the DG model. module case, you can kind of win because you understand homotopy limits better than you do in arbitrary things. You can calculate them via tote. And tote for DG modules is kind of a pain, but it's not as much of a pain as tote for spectra is. So you can kind of win. That's the point here. So here's the DG case. So let's let K be a field. Arbitrary characteristic. You have to be a little fiddly for characteristic 2 on occasion. So for x bounded below the module, there is a quasi-isomorphism module of the following form. So from coTHH of the co-free, co-commutative, coalgebra X to the co-free, co-commutative coalgebra on X cross the d-suspension of X. And this guy wants to be coTHH with respect to the product of X. So that this really is like this theorem when I get to kill my homotopy limits and everything is happy. The homotopy limit ate the dot. What happened? We have to think a little bit about how to prove this. And then this functor, all of our sort of niceness conditions tell us that this is going to be the same thing as the co-free coalgebra on X tensor with the co-free coalgebra on the d-suspension of X. So here you can really sort of unpack what's going on here. I should say that in the non-graded case, the same result was obtained by Fahrenheit and Solitar. If you wanted to do unbounded things, and you're sad. The reason that you're sad is because when you're trying to understand tote here, you run into issues where, like, as long as you have finitely many direct summing things, you can think about them as products and coproduct, as either a product or a coproduct. Like finite direct sum is both product and coproduct. But once you have infinitely many things, this is a problem. And in unbounded things, then you're taking totes of like infinitely many things in them. I should have specified when I said I wanted products and coproducts to be equal. I really wanted finite products and coproducts to be equal, and I can't reach that high, so I just have to think about it.
Can I ask a quick question?
Yes.
I missed the definition of this coTHH sub X.
So
I said
yeah,
it, but I just.
this is supposed to be a product sign and not an X.
Oh.
So it means that if I, like, in algebras here, I have a diagonal map from X to X cross X, and so that makes it a coalgebra with respect to that, and not with respect to my whatever my tensor product was. So I can define the same cosimplicial galaxy. That's what I mean. Okay. So great. So this is what happens in the DG case. You should think like, this is some sort of crazy thing, but like it actually happens. Things work out when you're in this nice algebraic context. All right. So now I'd like to talk about spectra, right? So what happens in spectra? Well, what about spectra? So as I already alluded to, code is harder to understand. So especially here, if we're restricting to the case of bounded chain complexes, we can really sort of like write down exactly what a formula for tote is, and then especially if you're Stephanie, you can like, you can just do it. Stephanie's really good at this. And sort of sort out exactly what happens and where your characteristic has to be not to, and all sorts of good jazz. So, but in spectra, like, you know, you can't just like work with the elements as hard as you can. Doesn't work. So that's a problem. And then in the current setup that I've been talking about with the symmetric, with the model category stuff, the fact that that products we can be equivalent to wedges, but not actually isomorphic. Let's just say it's a headache. You have to like think about things in a different way. So there's an obvious potential solution here, right? Which is that I should work in the world of infinity categories where I don't know the difference between isomorphic and weakly equivalent to or something like that. So work with infinity categories to solve this one. And that particular issue, I think you can solve it this way. Maybe I'll say a few more words about that at the end. Depending on your case, you might have found other headaches. So, right. So, what does that leave us with? Well, that means that, like, so maybe I should say that what about spectra, in the real answer here, is that this doesn't fit into the nice co-free, co-commutative, co-algebra functor schema. So in particular, I don't have like this kind of a theorem here because I don't have this kind of a functor here that I need. So maybe even if I could analyze my homotopy limits, I might still be sad. But all is not lost. So we don't have this theorem that I'm erasing. But we have an analogous result to this result right up here, but at the level of homology instead of at the level of things. Spectra, I guess. So let me tell you what this is. So, but in order to do that, let's make the following note. So I've been muttering about co-free, co-commutative, co-algebras on things, but I haven't really told you what those look like. I mean, I gave you some sort of general definition, but they might look, which might look sort of scary, but in fact, co-free, co-commutative, co-free graded, co-commutative coalgebras are things that we all like.
Really?
Yeah, totally. You're gonna love it, Jasper. So, co-free, graded, co-commutative. Okay, in my notes I wasn't quite that enthusiastic. I said they are familiar, but I think you're gonna like it. Co-algebras are familiar. In fact, they're the underlying coalgebras of classical Hopf algebras. You like Hopf algebras?
Sure.
Yeah, all right. So if I want to take the co-free divided power algebra on the same generators in the same degree. And similarly, the co-free, co-commutative, coalgebra on generators in odd degrees so you get the underlying coalgebra the stereo algebra. On the same generators in the same degrees. So this is great. It does lead to some terminological mismatch, right? Because I'm going to tell you that I take a co-free, co-commutative coalgebra on some stuff, and I get a divided power algebra, and you're going to be like, seriously?
Can you explain what, or say something about why?
Yeah. So actually, you can maybe kind of see from my sort of generic definition, you could see that it was sort of built out of the tensor algebra. And that's fundamentally what's going on, is that the tensor algebra, if I didn't impose commutativity in any way, then the tensor algebra would really also be the tensor coalgebra, and my co-multiplication would be like divide up all the tensors in all the ways you can divide them all up, right? And then you check that when you impose the co-commutativity stuff, this is what pops out. And you know, graded is what gives you the exteriorness for odd degrees in the usual fashion. So it's sort of a psychological mismatch because the co-free coalgebras are algebras. That's what their names are. But it's really a good thing because it means that, you know, we know what they are. They're not some sort of like abstract crazy thing. I guess my presentation today has been like, let's do abstract crazy things, and then I've been sort of like trying to zoom down towards things that are very concrete, which is maybe not ideal expositional style, but you know, I was a Peter May student. Sorry. Alright. Okay. So what do we know? We know that we know about the co-free graded co-commutative coalgebras. Like they're things that we like, we know their names, we can write them down. So with that in mind, I would claim that the following theorem is the homology level result that's analogous to the theorem that I've just erased. So you see is a co-commutative coalgebra spectrum. That is cofibrant. As a spectrum. Yeah. And whose homology coalgebra is co-free, co-commutative coalgebra on stuff in even degrees. So that means that I'm going to say is a divided power algebra, right? So I'm going to work over FP here. Divided power algebra on a bunch of classes. What do I need to assume about these classes where xi's are in non-negative, or 0 and the even degrees? So that makes good on my claim that this really is a co-free, co-commutative coalgebra. only finitely many xi's in any fixed degree. Okay, so if we have this, so we know what our homology coalgebra is, and it is a co-free guy, then we have the following isomorphism. P models from the homology of the topological coHochschild homology of C, coefficient in FP, to the divided power algebra on all my generators, so the same thing I started with. Tensor, interior algebra, control FP, on one hat, C hat, and so on and so forth, where the degree of xi hat is the degree of xi minus 1. So what's up here? This is our co-free, co-commutative coalgebra that we started with, and this is the co-free, co-commutative coalgebra on shifted down, on the same generator shifted down. Right, so this is C on x1, x2, etc., and this is C on the suspension of my subculture. So that's why I want to think about this as being the homology level and not an analog of the previous theorem, right? So I'm saying that coTHH from the eyes of homology is if it was free, co-free to the eyes of homology, then it splits up as the thing that I started with, the co-free thing, and then the co-free thing on the shift down, which is exactly what I had in the TG. So great. So where does this come from? Well, this comes from a spectral sequence. And in fact, it comes from the collapsing of the spectral sequence. I guess while I'm talking about analogies, if I chopped off all my co's, then I would get an analogous result, but instead of descending, I would descend. Okay, so this result comes from the collapsing of a spectral sequence. So there's a coHochschild spectral sequence. So Bob told me that John was not allowed to put co in front of people's names at some point. But it's really unfortunate that you hadn't talked to Doy because you put co in front of Hochschild in like 1980, which was before this was disallowed. And so, if only you had known.
Otherwise you have to ask myself if it's okay.
But it's so much fun to say. Alright, so there's a coHochschild spectral sequence. What does it look like? E2 is given by the classical Hochschild homology of the homology of your cone algebra C, FP coefficients, and it wants to converge to the homology of coTHH and C.
It's not coHHH.
It is, I always do that. Thank you. Yeah, that would be weird. Yeah. Yeah, I messed up in my notes. So for, with our conditions here, so for C, a coalgebra spectrum. That is cofibrant. I suppose I sort of alluded to this before, but I didn't really talk about it. But one thing that goes maybe wrong here in the model category land is that there isn't nearly as nice, or maybe there isn't even a model category of coalgebra spectra that you get to talk about, like being a cofibrant coalgebra spectrum in. So I really mean cofibrant as an underlying spectrum. Because like, there's a bunch of problems with tote and smash product. They don't like each other. So like all the things that you did in, say, EKMM, they don't just go. Okay, so, right, so this is a coHochschild spectral sequence. I was like fairly sloppy about this arrow, right? And that's because this is an instance of the Bouchfield conspectral sequence for the cosimplicial object, coTHH. And so Bouchfield conspectral sequences sort of don't get to converge for free. So convergence not automatic. So we proved that it converges under some nice conditions. And maybe in particular, it's relevant to say that if my coalgebra spectrum is the suspension spectrum of a simply connected or a nilpotent space, you do get convergence. So like for suspension spectrum of X, or X is nilpotent or simply connected. Great. So, alright, so then we sometimes, like, many of the cases we know about, this is really going to converge. And then one can further show so that this is really a theorem, harder than it looks, that in C, in the theorem I guess I've just, or maybe in this theorem up here, the spectral sequence one, this is co-commutative. And this is a spectral sequence of coalgebras. So by which we really mean there is a co-Leibniz rule. For the differentials. So it would be really nice if this were very straightforward, but actually proving this, proving that you really get this, is you have to really unpack how pairings and products work on the Bouchfield conspectral sequence. And it's sort of, they work much less beautifully than pairings and products on some other spectral sequences. There's some serious we have to end up passing through the Joule-Kahn theorem. And it becomes rather messy. But you get it, and so then the co-Leibniz rule tells you that allows you to conclude that if the E2 page here, if this is co-free and things are concentrated on even degrees, then the differential is sufficiently restricted that you have to get a collapse result. So this implies that so let's say when the input to the spectral sequence is co-free on even degrees, the spectral sequence has to collapse. So, great. So then the spectral sequence collapses, and so our result about if I plug in a co-commutative coalgebra whose homology is like the divided power algebra, and I want to try and understand what the homology of its coTHH is, it really is just so you calculate what happens to the homology, the coHochschild homology of your divided power algebra, and you get exactly like the thing and its desuspension. So then you're good. So that's where the theorem came from. So here's an example. So what's a space that you know that has nice homology? Well, maybe UN. So the homology of UN is going to be divided power algebra on a bunch of classes x1, xn, where xi is in degree 2i. And so applying the theorem, you find that the homology of its coTHH which is really the homology of the free loop space, is just this divided power algebra implementing exterior algebra on to shift down all classes. So maybe you knew this before, but it sort of falls immediately out of this collapse result. You have to work not at all with this, so it's kind of a nice thing. And so anytime you have a space whose cohomology is a polynomial algebra on a bunch of things in even degrees, then you can play this same game and get a similar kind of result for the homology of the free loop space, i.e. homology of coTHH. Okay, so what next? So maybe I alluded to the fact that there are some problems with these model categories of spectra, right? Like the model categories of coalgebra spectra are not solving all my problems. And so in joint work with Tina and Brooke, we're trying to sort of make sure that the infinity category foundations are in place to talk about coTHH of co-commutative or just coalgebra spectra in an infinity context. More or less there. And so what does that buy you? That buys you the ability to say things like, if C is a co-commutative coalgebra spectrum in the infinity category spectrum, then its coTHH is going to be a coalgebra spectrum, which, that's what's supposed to happen for THH, right? If I take THH and I shove in a commutative algebra, I'm supposed to get another commutative algebra out, and then I can keep going forever and ever and ever. So you can't show that without sort of working in this infinity category context. Maybe we didn't try as hard as one could, so that's one thing you do. And then from that, so you can get more structure on coTHH itself, and then the idea is to push this structure into the spectral sequence and sort of have more things you can do to compute more things. Thank you.
locally is just an entirely extension of a free thing. So do you have a notion of coatonus or co?
We think that that's a thing that one might try to think about, but we haven't thought about it. Yeah, so we don't yet.
So you don't have an interpretation for the desuspension as sort of just coming from some cool
No.
differentials or?
No, that would be nice.
So, like a situation that's not quite as bad as spectrum, but still bad, is when your basis is not a field. Can you make any kind of analog for the coTHH that uses the derived tensor product, or?
Probably, I don't know, I don't have like concrete things to say in that particular case. That doesn't mean you can't.
Am I right in remembering that the only way that the Gauss transmetal sequence can fail to convert is that it has a derived infinity page? Anybody?
There's a lot
Because
of
you show it collapses, right? So,
Yeah,
So that can't
but that's
be-
not, I think that's not enough to show that it converges to the thing that we want it to converge to. That's what Brooke says.
Yeah.
I mean, it converges to something.
It converges to something, but it might not, but we might not be able to identify that as the homology of coTHH, which is like our main goal in life.
I mean, if there's a fundamental group, for instance, it's like Landsberg-Moore spectral sequence. It doesn't have to converge if there's a fundamental group does not act neutral in the amplifier.
I think that's a different issue.
This took a slightly long discussion, so.
50 years ago.
So maybe we should thank